Welcome to Quantum Computing Essentials Part 1, Lecture 4. So in the previous lecture, we have seen basically detail about the vector space, some definitions, and little bit about the span and the spanning sets, and also the definition of the vector subspaces. So today we'll be covering some more parts, mainly the four fundamental subspaces. Four fundamental subspaces. So what are these four fundamental subspaces? The first one is known as the range space. The second one is the row space, or the row subspace. There is another name for the range space, which is also known as the column space or the column subspace. And there are two null spaces. So we will look into the two different null spaces while we'll be discussing in detail. So there will be two null spaces. Okay. So there are four fundamental subspaces, and they are very much important because many times we'll be designing the algorithm where we need to compute certain kind of operator that can project or the rotate a particular vector to another vector. So say one plane to another plane, that rotation or that projection can be performed using the matrix product of a particular vector with the range space or the null space. So for those kind of things, actually we need to very much clear about these four fundamental subspaces. So let us do a little bit detail. So the first one is the range space. So say for example a matrix which has the elements of size m cross n, and they are the real elements. And a range space is defined as the subspace Ra, that is known as the column space of A or the row space of A. And so it belongs to the region row space of each of Rm, which is generated by the linear transformation f of x bar equals to A into x bar, that is the right hand product of the vector with the matrix A, and it is defined as R of A, that is the range space of A. We will see the geometry later on. Is defined as the set Ax bar such that the x bar belongs to the set Rn. Note that this particular vector will belongs to the set Rn, set of real numbers of dimension n, whereas the range space of A will be the set of element in the dimension of Rm. So this is the definition. So that means R of A will belong to the set Rm. And with direct notation, so we can write this as A as an operator, ket x is the vector. Similarly, this we can represent as A into ket x. Ket x is the quantum state vector, such that all the state vectors belongs to the set Rn. And this will be obviously same. So this is also known as column space of A, column space of A, and hence written as call of A. The fundamental concept is RA, that is range space or the column space of A, is spanned by, this is the very important term, it is spanned by the columns. So in short notation, I am writing as col n, column of A. So that is, if I multiply A with the quantum state ket x or the vector x, so I should look into the element. So this A matrix, I can write it as the ket A1, ket A2. They are the columns. Say for example, along this is the column, this is the second column, and there will be n such elements, and the last column vector will be ket an or the n vector, and it will be multiplied with the vector ket x, such that the element of ket x are x1, x2 to up to xn. So what we are doing is that we are seeing the picture in the column. That means the column of A, they are multiplied with the vector. So that is called the range space of A, that is spanned by the columns of A. So that is the most important part in the column space or the range space. So now we'll be looking at the part, the second fundamental subspace known as the row subspace or the row space. So similarly, if we have the matrix A, say for example, I take a matrix like this. So the first element is, say for example, A11, A12, and up to, for example, I consider there are, so if A belongs to the set of Rm cross n, so what does it mean? That there are m rows and n columns. So the last element will be A1n. This 2-1 position element will be A21, up to there will be AM1 element. And if we write all the elements, so the last element will be get AMN. So this is the matrix. Now if we do the E transpose, so there will be a transposition operations on A, and A transpose will have the dimension of Rn cross M okay, such that the columns will come into the row and row will come into the column part. So then the range the range the range of A transpose, the range of A transpose, it will be the subspace of Rn, because right now the columns, how many columns up there in this A transpose? So earlier there was there was m number of rows and n number of columns. So if I do the transposition, then basically the number of column will be n and the number of row will be m. So obviously the range of A transpose will belong to the subspace of Rn as A transpose belongs to the set Rn cross m. So then basically we can define it as the range space of the range space of E transpose. So range space of A transpose means the row space of A, and we can write it as the set A transpose Y. So we're multiplying the vector Y as a right product with the A transpose, such that the vector Y or the quantum state Y belongs to the set Rm. Why Rm? Because I have n cross m, so I need the length, the dimension of Y to be m cross 1, such that my R A transpose belongs to R n, just the opposite of the range space. So there are certain notes in this part. So let's see the notes. So first note is that if there is an element B which belongs to the set range space of A, then what we can do, I should be able to write B equals to I should be able to write B equals to A ket x for some vector x. So that means obviously this B should be a vector. So if ket B is an element of Ra, then ket B should be able, I should be able to write ket B equals to A ket x. And if there is another element, A belongs to the set R of A transpose, then it implies that I should be able to write it as A transpose equals to A into some ket y. So it should be better to write it as it should be better to write it as the Y transpose with the operator A, where Y should be state vector, and A should be another state vector. So I should be able to write in this way. For some vector state Y. So this much is about these two fundamental subspaces, the column space of A and the columns and the row space of A. And once we know that the row reduced echelon form of a matrix, so there is another note. So keep it for the time being. We may later discuss about this echelon form and the how to find out the rank, how to diagonalize a matrix, those things. So then actually we can have a much bigger version of this. So keep this note. So first point is, so if A is matrix which has the dimension whose elements belongs to the set this, then if we do row reduced echelon form, row reduced echelon form, and suppose we get a matrix U, then the spanning sets, then the spanning set, there will be two sets. The first set is the non-zero rows, of U. They should span the R of range of A transpose. That means the row space. That means the row space. And the second spanning set, the basic columns in A, which actually determines the ranks. We will later see this part. The basic columns in A, it should span the range space of A. That means the column space. So remember that suppose for a matrix, say A is a matrix of this kind of structure. Say all the elements are non-zero for the time being. But as it is a M cross N matrix, right? So obviously the rank will be minimum of the M and N. Okay, so suppose these are the elements of the matrix. Here I have taken a 3 cross 4 matrix. Suppose this is the A, and if we do the row echelon form, then we may get a matrix U of the structure like this. Suppose this is some element. So it is row reduced form. So obviously, suppose the structure is like this. And maybe say for all other elements are 0. Okay. So how many basic columns are there? So say this is suppose non-zero. Okay. So obviously there is you can see the pivot elements are here, here, and here. So 3 basic columns are there, right? So it is a rank 3 matrix, and obviously from this information,
we can say that the non-zero rows of U span A range space of A transpose, and the basic columns, there are three basic columns in A. So what are the basic columns here? This one, and this one. So basic columns in A span the range space of A. There are two null spaces. Let us see that. Then we'll discuss a little bit about the geometry of this subspaces, for fundamental subspaces, and some more details. So null spaces. So obviously, we can write these two null spaces. The first null space as n of A, and the second null space is the n of A transpose. Okay. So let us discuss about them. So for a matrix A, say for example, it belongs to the set R m cross n, then the set n of A defined as the vectors x such that A into ktex equals to 0. So A into the vector. So they are the elements, the set of vectors. Those vectors, if we write multiply with some operator, it will give me the 0 vector. So obviously, this set will belong to Rn. Okay. As you can see that it should be, if the matrix is A is m cross n, then n has to be n cross 1 to make it m cross 1. This 0 will belong to the set m cross 1 m. So which together will make this n A, the null space of A should be Rn. Then the set n A is called the null space of A. And this is a very important part, because when we'll be trying to design algorithms, say for example least square method, and we'll see that this null space of A is very important, because that is the space where we get the minimum error. Okay, so if we take the dot product of our observation vector with the null space, we get the minimum error. So we'll come into this part later on, some regarding certain applications of this. So for the timing, let us stick to the definition. The second set, null space of A transpose, this particular set is defined as the set of vectors y, such that A transpose k to y will produce the vector 0. And very important part here is this 0. So earlier, as we multiplied m cross n with n cross 1, we get m cross 1 0. Now A transpose will be m cross m, for which y should be m cross 1, and as a consequence of this particular 0 will have the dimension Rn. So they are very different. This 0 and this 0, they are very different, and we need to carefully see these things while designing algorithms, because that will give us the dimension of the data set. So wrong use of this set will give us the information loss or the bias in the estimator. So these are very much important. And obviously, this as a consequence of all of this, will get the dimension of n of A transpose, this particular null space. So this null space, so from here, actually, you can see that it should be Rn. Okay. So say, for example, if I take a matrix of 3 cross 2, a matrix, obviously the rank will be either 2 or 1. Okay. So it should be minimum of 3, 2. And so at most the rank will be 2. So now you can see the m will be 3, and here n is 2. So your null space of A will have it's a 2-dimension set of set in the 2D, and where it is the set in 3D. So they are very different. So that means the null space of A transpose is the set of all solutions to the left hand. So it's a note, keep it as a note. So null space of A transpose is the set of all solution to the left hand homogeneous equation. So I am writing in short as homogeneous equation Y transpose A equals to 0 to match the dimension. Because the dimension of Y is how much? M cross 1. And A should be M cross N. So together I'll get the 0 in Rn, right? So because M is, so it should be 1 cross M. It should be some M cross N. And I will get as 1 cross N. So obviously this equation and this equation is the same equation, just a different form of this. So let us take some more notes on this particular part, which may help us at a later point of time. So first is that if A is the set belongs to R M cross N, then number 1, null space of A is the set of element 0. Here 0 is a vector, note it. It is not just 0, it's a vector. That means there are, so suppose for example, if just for simplicity, if 0 is a 2-dimensional 0 vector, then it is actually 2 zeros. Okay. If it is a 3-dimensional thing, then it will be 3 zeros. Okay. So it's a vector actually. So the null space of A is the set of 0th vector if and only if and only if rank of A equals to n. Okay. These are two very important statements. Next is the null space of A transpose is the set of 0 vectors if and only if rank of A equals to M. That's very clear from the dimension of the 0th vector, because here the dimension is n. Then should, because the rank will be the minimum of m cross n. So 0 vector is that here the dimension is n, here the dimension is m. Obviously the rank will be the opposite to actually consistent with the definition of rank. There are some more notes. I'm not giving it right now. So let us see the geometry for the time being. So geometry of these subspaces, fundamental subspaces, which is very much important here. So let me first draw it. This geometry is very much important. Then there is okay. So this is the range space of A. I'll talk about the dimension later. So this is the range space of A, and this is the range space of A transpose. So I'm writing outside to make it a clear one. So range space of A transpose, this one. This one is the null space of A. So null of A, and this is the null of A transpose. I'm writing in short, n of A transpose. Okay. So suppose there is one vector, and I want to take the transposition of here to here. Okay. So obviously, if I want to, if there is a vector x, okay, so I want to go to range space of A. So basically, I write it as Ax equals to B. That is my linear equation. So I multiply it with the x, then I get the element B. Okay. So what is happening here is that the dimension is R. Okay. And so this part is the Rn. This part is the Rm. So I'm writing in that all this picture in 2D, which is actually not the case. So this part actually is in the M dimension. So there is an arbitrary distinctions. Okay. And suppose this is M dimensional, some hyperplane or some spaces is there with M dimension, and this subspace, suppose for example this is in Rn. So because this range space of A transpose belongs to Rn, and null space of A, not A transpose, belongs to Rn, whereas the column space of A belongs to the set Rm, and null space of A transpose. This difference, this A and A transpose, to keep a note on this. So the interesting part is that if there is a vector x, and so I want to go from this side to this side. This x is, suppose if it is n-dimensional some vectors, suppose it is xn, some n x vector with the with the dimension n. So I can clearly write it as this. So ket x, and this ket x actually, say I'm writing it here n. So it's an n dimensional vector such that a into ket x produce zero vector, and this zero vector will have the dimension of m, right? So basically this is the part, and here actually I'll get the full rank. So if this vector x is of dimension r, then basically for rth dimension, the product of ket x into a will give me the product b, and this b will have also the dimension m. So because there is a theorem known as the rank plus nullity theorem. So I did not discuss about the rank, but at some point of time, there will be another lecture session on rank only. Okay, then I'll give a detail on this part. So just keep a note on this theorem. So rank plus nullity theorem. Nullity theorem. So the theorem says that the dimension of range space of A plus the dimension of null space of A will be equals to n for all A belongs to R m cross n. Okay, so this theory, there is a corollary or the reduced form of the theory, which can be written as that the rank of a matrix, because rank is the basic number of columns, right? So rank of a matrix, rank of A will be equals to n minus your dimension of null space of A transpose, or you can write it as m minus, so there is a little mistake. So this is n minus dimension of A, which is also equals to m minus of dimension of n of A transpose, because the null space of A has the element, if it is zero vector, then that will also belongs to the set Rm. So I should deduct this part from M. And null space of A, this belongs to the set of Rn. Then obviously I should take minus in the same dimension, n minus n, and that will give me the rank A. Okay. So, and they are actually the dimension of range space of A, because dimension of range space of A is actually the basic number of columns or the number of pivots in a particular matrix. Then obviously it should be equals to rank of this matrix. Here the dimension of the range space of A, if it is equals to R, then it should be the rank of the matrix A. So for the time being, I am keeping it here for the today, and in the later part, we'll be discussing about little bit more about the Hilbert spaces and the inner product space, as well as we'll go for the diagonalization techniques. Okay, so so for a simple example or a very short example, let us discuss the least square method as an example here. So what do we do? A least square method, least square algorithm. So for an example, that how actually this subspaces are important. So we have some equation X equals to B, and say for example, M is some M cross N matrix. This X vector is some N cross one vector. Write it in the Ket form. And this B vector, Ket B, is some vector of dimension M cross 1. Suppose somebody asked me to solve these equations to get the values, the vector or an estimate of Ktex, maybe in presence of noise or in absence of noise, so an estimate of that. So as it is a rectangular matrix, so we cannot compute A inverse, right? This cannot be done as it's a rectangular matrix. First of all, even if it is a square matrix, then again we have to check the condition number and all those things. So basic criteria, what we do is basically we do this particular technique X minus B. So all the error between the elements in the plane of A, so we minimize in this order. So we take the Euclidean norm minimizations of this for all values of X. And what we get is that there is a pseudo inverse of A, and the form of the pseudo inverse is like this: A inverse A whole transpose A. So we at some point of time we may discuss a little bit more about least square method. So for the time being, it's the pseudo inverse. Okay. So say for example, this operator I call it as a P. Then I get the solution, the estimate of X as P into your B, Ket B. This is the solution. That means your pseudo inverse, this part, that is A inverse A whole transpose A into your Ket B is the solution. This is the algorithmic solution. But what is the actual thing happening here? Okay. So this is the result, this is the solution, and there is an error actually. And then the error is actually your identity matrix minus this part, P into Ket B. Okay. So what is happening here is that so suppose we divide the space of A like this. Suppose this is the column space of A. Okay. And suppose this one is the null space of your A. And we have some observation vector B, right? And as this equation is not a convenient equation because we cannot take the inverse of A. And say, for example, due to noise, this B vector. So if it is a full rank matrix, this B vector should be on the plane of column of A. But as there is problem, means there is noise and the matrix is not a square matrix, mostly due to the noise, this vector will be in a deviated positions. Suppose this is the B vector. Okay. So if you take the projections of the B vector on the column of A, if you take the projection over here, this vector, so suppose column of A. So if I take the dot product between B and the column space of A, whatever thing I will be get, that is the Ktex part estimated. Okay. This particular part is geometrically this part. And this error part, if you take the vector multiply, or if I take the projection of this particular B vector on the null space of A. Okay. So if I take the projection in this plane, so whatever the value of this particular line segment, so that is the error part. This is the error. And this is the estimated value. Estimate. I am writing in short as estimate. Okay. So many algorithms, because we will be in the quantum computation part, will be mostly working with the linear operator and finding the estimate of certain parameters. for which we'll be taking the multiplications of certain operators with the quantum state vectors to evaluate its quantum evolution. So the importance of column space, the range space, the null space of A and null space of A transpose will be very much useful, and we'll be discussing more on this part. So thank you for the time being. So see you in the next lecture.